hello everyone. Very happy to be here. I'm very happy to join Conf42. My name is Zhang, and today my topic is maximizing error injection realism for chaos engineering with system calls. So of course we can replace maximizing with improving here because I can't see like I have maximized the error injection realism. But it's still interesting to explore like how to improve the realism for chaos engineering experiments. So about myself, currently I'm doing my PhD study at KTH, Royal Institute of Technology in Sweden. And before that, I was a software engineer at Tencent in China. And I'm very proud to say that one of my main research topics is chaos engineering exactly. So it's really nice to join the conference such as Conf42 and discuss all kinds of novel findings of chaos engineering with everyone here. So today, yes, so during my research work, I found like there are lots of nice talks, tutorials, and also nice tools. And I found that people also talking about like the challenges of chaos engineering nowadays. So for example, here are some challenges I found. The first one, how to evaluate different aspects of resilience. Because chaos engineering can be done at different levels, like operating system level, network level, or application level. And then we need to like have extra observability of an application and collect different kinds of metrics so we can like precisely define how our system behaves during a chaos engineering experiment, and how to evaluate the resilience of an application at different level in different aspects can be quite challenging. The second one, how to automate the chaos experiments. Though we have lots of awesome tools today, like they do help a lot for chaos engineering experiments, but still like how based on the application's concrete scenario, how to make this automation really helpful and efficient for developers. This can be quite challenging, like how we automate the flow, how we learn from the chaos engineering experiments automatically, and how we use the learned knowledge for our future chaos engineering. So this still can be challenging and need more research work on that. And the third challenge, how to improve the efficiency of chaos experiments. So for example, if we are going to explore some really large fault injection search space, like we have a lot of different combinations to inject different kinds of failures in production, but given the limited experiment time, we can't really explore every possibilities. So how to improve the efficiency of this chaos experiments, how to learn as much as we can during an experiment, this can be challenging, and to explore this can be quite helpful for like our future chaos engineering experiments. And today I would like to only focus on the third challenge, how to improve the efficiency of the chaos experiments. And I believe that there will be lots of different like directions, different solutions for this challenge. One of the idea we come up with is to synthesize realistic failure models for chaos engineering. Because let us take an example. If we have we have lots of different failures to explore, and the experiment time is quite limited, and also this will be done in production, so it's sort of risky if we inject so many different kinds of failures. Especially some failures, they may not actually happen in production. So how to synthesize realistic failure models that actually it's possible to see like these errors in production. And then we use chaos engineering experiments to explore more, like to learn more about how your system behaves under such an error, such a failure. This could be quite interesting. And then we can learn more in a limited time. So based on this idea, we would like to do some more research, and to be precise and to do deep research, we would like to narrow down the scope. So we want to focus on system call invocations at this moment. But of course, this idea can be like used and explored at other levels. For example, at application level, we can also like synthesize exception certain like failure models with respect to Java exceptions, and then we try it in chaos engineering experiments. That should also work. But today I would like only to present our research work at the system call invocation level about how to synthesize realistic failure models for chaos engineering experiments. Yes, and next, before going into any details, I would like to show you a short demonstration so we can have an overall picture of system call invocations and also about these naturally happening errors at the system call invocation level. First of all, about system call. So system call is a fundamental interface between an application and the operating system, or let's say the Linux kernel. And usually the critical resources such as network or disk storage or maybe like thread scheduling, etc. These resources are controlled by the operating system kernel. And then when an application needs some resources in these categories, the application needs to invoke some specific system calls. So the application invokes system calls. It transforms the control from the user space to the kernel space, and then the kernel can arrange the resources for the application. So in Linux kernel, there are more than 300 different kinds of system calls, and also Linux provides more than 100 different kinds of error codes. So the Linux kernel can precisely report different kinds of errors when a system call invocation fails. So imagine this is quite a big combination. Like we have hundreds of system call types. We also have hundreds of error codes. If we want to do some experiments at system call level, if we want to inject some system call errors on purpose, then it's quite time consuming if we try to combine different system call types with different error codes. And actually some of the combinations are not realistic and they can never happen in production environment. So we need a better strategy to generate some error injection models, and then we can pick up the most interesting errors to inject in our system and learn about the resilience. Okay, so about the demo, now I'm going to switch to my terminal. Yes, so here we have Mount. We have a script to monitor all kinds of system call invocations for us, right? Currently, I'm using OBS, a software called OBS, to record this video. And when you watch this video or listen to this video, I believe that you won't feel anything abnormal. Like the pictures, the videos are good, and also the sound is quite good. So this means the OBS is functioning correctly. And behind this, we can feel the OBS must interact a lot with the system, and it invokes lots of different system calls. So let's take a look at this. There is a script called system call monitor, and then given the process name OBS, I would like to use milliseconds as a unit, and I also want to monitor the latency of different system call invocations. And please report all the metrics every 1 second. Okay, so now we can see yes, the OBS indeed does lots of system call invocations, and the type is here, field text, read, write, etc. And different counts of the system call invocations, and also most of the system calls succeed. But still we can see some of the system calls failed, and we can see the percentage of these failures. Let's see, so behind this field text system call, we also had field text E again, and also let's see, yes, most of them are field text, but if we keep watching this for several, maybe 1 or 2 minutes, I think we will have more failures to observe. For example, this one, EXECVE, it failed 4 times in 1 second, and all of them return an ENOENT error code. So this is just an idea, we can feel the presence of system call invocations behind one application. Every application indeed does lots of system calls, and some of them failed naturally. So this is the idea first, and if we want to make it a bit more complex, so for example, we keep monitoring the application, and we keep extracting these metrics and put them into the database. So in a long time, we can have a series of monitoring metrics at the system call level, and then we can have really diverse information about the natural happening errors at this system call invocation level. So for example, this one is a dashboard. We deployed an email server into production, and we just keep it running as usual. And we also register different email accounts into different mailing lists. So we do collect some natural traffic here. And then by attaching the system call invocation monitor, we can collect the metrics like the failure rate, the total number of system call invocations, and also the latency of the system call invocations, etc. So you see here, there are many different kinds of system calls failed with different error codes, E again, E corner reset, etc. And this can be quite helpful and interesting for us to see, okay, even though the email server is functioning and still we have lots of different errors at the system call level, and they return different error codes. And also the failure rate are quite different. Sometimes they failed a lot, and sometimes it's really rare to observe one single error in production. So this is the question to be discussed here. Because these are errors, so an error can be handled by the operating system. It can be remediated. But if the operating system cannot handle this error, usually it wraps the error and reports it to the application. For example, if some system call invocations failed and the Linux kernel cannot handle it, it can wrap it as a Java exception. And then in our Java application, we can write a try-catch block to handle this concrete error scenario. So interesting question is we are not sure if these errors happen more frequently, because sometimes it's rare to observe one error. But if this error happens far more frequently, in a severe scenario, how our application behaves, then it can be quite interesting to explore this using chaos engineering experiments. Okay, let's come back to the slides. So that's why we would like to do some research at system call level, and also about analyzing the realistic errors and generating the realistic error models for error injections. We call it Phoebe as a research type, and this is an overall picture of the design of Phoebe. So we can start from here. We have application in production. We just deploy it normally, and then the application interacts with the kernel space using different kinds of system calls. And then Phoebe attaches two different kinds of monitors here. The first one is natural error monitor. So it uses this, I will introduce later, we have some nice features. We use some nice features provided by the Linux kernel. So it observes different kinds of natural errors, and then it reports to our error model synthesizer. Also, there is another monitor called application behavior monitor, because we do need some application-specific metrics like response code or maybe some performance-related metrics, the CPU usage, heap memory usage, etc. Because we would like to compare how the application behaves when an error is injected. We need some evidence about the steady state. So based on this monitored information, the error model synthesizer outputs some realistic error models based on the naturally happening errors. And then our Phoebe's orchestrator can conduct some chaos engineering experiments. It uses a system call injector. So this injector intercepts some system call invocations, and then it replaces the return code with our predefined error codes. And so we get finally a resilience report about how the application behaves when we actively inject some specific errors at the system call level. And of course, we can visualize the results using a visualizer, just like I showed you before, a grandfather dashboard, which provides you some information about system call invocations and error rates. So a question here is how to synthesize realistic error models. Now we have got natural errors, and we have also we can also analyze these errors, like what's the error rate, what is the error code, etc. And then we have to use different strategies to generate realistic error models. And here our idea is to amplify the error rate. So because given a limited time, we would like to learn as much as we can in a chaos engineering experiment. So we need to somehow amplify the error rate, but we still keep it realistic. This can be done like we keep the type of the system call as the same, and then we slightly increase the error rate, the happening rate of this specific error, so we can observe enough data in a chaos engineering experiment. Before doing that, I would like to propose some definitions. So system call invocation error, we define it as here as follows. An invocation of a system call is deemed an error if it returns an error code. And then we need to define the monitoring interval, because we keep reporting this metrics to our database, and this is based on the monitoring interval. So a monitoring interval is a period of time along which metrics of interest are collected. Based on these two definitions, we can define our error rate. So the error rate means the percentage of the errors with respect to the same type, the total number of invocations in the same type. So for example, in 1 second, there are 10 open system calls, and one of them failed with an error code, for example, no content or something like that. Then the error rate can be 10%. And then this is some information for us to generate error models in the future, because we can amplify this error rate. This error rate was observed in production, so it can be a basic information for us. Yes, and talking about the application strategy, we have some strategies predefined here. So if we have a set of error rates with respect to error system call error code E, and then we can calculate the maximum value of the error rate in this observation phase, and also the variance of the error rate. So if the max value of error rate is quite low, this means it's pretty difficult to observe such an error in production. It's rare to see this error, and it does not happen so frequently. Then we categorize such errors into sporadic errors. And to observe these errors and to learn more about how our application behaves under these errors, we would like to use a fixed error rate to amplify this error rate. So this can be predefined, of course, and usually we just use a number that can be large enough for our chaos engineering experiments, so we can get enough data and we can evaluate how our application behaves when this error happens. And also there are also different errors. These errors are quite fluctuating because the max value is relatively large, so we can observe these errors in production more frequently, and also the variance of the error rate is larger than a certain value. So this means sometimes this system call invocation errors happen quite a lot, but sometimes it's difficult to observe them. And by amplifying these kinds of errors, we would like to keep using the maximum value of the error rate. So this error rate does exist in production, and then we keep using it, so we somehow improve the frequency of these fluctuating errors. And the last one, we categorize it as steady errors. So the maximum value of the error rate is quite large, but the variance of the error rate is not that large. So we can always observe these errors in a relatively steady frequency. So that's why we would like to multiply the max value with a factor, because we feel interested to increase the happening rate of these errors, just to see if there exists any threshold for our application. Like in production, this happens in this frequency. But if we do a chaos engineering experiments and we increase the error rate, how our application behaves, is it still resilient to this error, or there exists a threshold, like after this error rate, the application behaves abnormally, etc. Then we can use experiments to explore it. Of course, these are sort of like basic application strategies. We can also define more complex strategies, like we combine different scenarios, or we have injection, maybe injection chain, or considering the propagation of errors, etc. And then it's another story. So as a research prototype, we would like to evaluate how Phoebe functions when we use Phoebe to monitor system call and also inject system call invocation errors. So we have different evaluation targets. For example, this Hedwig. Hedwig is an email server. So I just show you during my demonstration, we deploy Hedwig into production, and then we use Hedwig to send and fetch emails in a normal way. So we can calculate the steady state, of course, and we can also have some realistic traffic there. And then we can, based on the sending and fetching emails, the number of failures, etc., we can know how the system behaves without injecting any errors. But based on our observation, we can still observe some errors that naturally happen in production. So for example, the table on your left, we observed this almost 10 different kinds of system call errors, and some of them happen quite a lot. Some of them, the error rate is quite low. But these are sort of interesting findings for us, and we would like to explore more about how Hedwig behaves if we inject more failures with respect to different categories of system calls. So that's the first phase. We observe the system's behavior, and we collect all kinds of naturally happened errors. Based on the error and also based on the application strategies I introduced just now, or Phoebe outputs realistic error injection models for our future experiments. And then we can keep injecting different kind of error, invocation failures, and then we try to send and fetch emails again to see how Hedwig behaves. And this is the result. So based on the result table, Hedwig does have different capabilities about bearing these injected errors. So some injected invocation errors, it directly crash the server, or it has a state corruption. This means even we turn off the error injection, the email server still behaves incorrectly. But some of the system call invocation errors, Hedwig is quite resilient to them. Even we keep injecting these errors with a relatively larger error rate than the original one, Hedwig is still resilient and provides the correct functionality. So this is some findings of the experiment on Hedwig. We also did some experiments on tTorrent. tTorrent is a Java client which is used to downloading files using BitTorrent protocol. So we still, as a normal user, we use tTorrent to download files, and then we observe tTorrent normal behavior and also collects all the naturally happening errors. And then based on these naturally happening errors, we generate error injection models for Phoebe for our chaos engineering experiments. And this is the result of the evaluation experiments on tTorrent. Similarly, we can also find that tTorrent is resilient to some of the system call invocation errors, and some of the system call invocation errors are quite critical to tTorrent's functionalities. So based on this resilience report, we can further explore how we can improve the application's resilience when such an system call invocation happens. We can also explore like what's the relations between system call invocation failures and the application's behavior or the exceptions in this specific application. So there are lots of interesting topics to see. And another important aspect is the overhead. Thanks to the feature we used in Phoebe, so now I'm going to introduce it a little bit. The feature is called eBPF. It's a feature like provided by the Linux kernel. By using eBPF, it's quite like easy to capture the system call invocation information, and you can also intercept the system call invocations to rewrite return code, etc. Actually, eBPF is quite powerful. You can use this feature to have a really nice observability of Linux kernel. And an interesting story behind this is I learned it when I joined Conf42 last year. There was a workshop which was about the Linux observability and chaos engineering, hosted by Conf42. So I learned a lot, and I learned like eBPF and other like the front end BCC are really helpful to improve the observability and get really lots of nice insights in our running system. So we came back to Sweden and decided to explore more on this. Then we came up with this research idea, and finally we write a paper about it. So it's really nice. Like we joined Conf42 to share with each other, and we learned a lot. And finally, I can come back again to tell you like here is my findings, and here is some extra work we have done in this year. So I think it's quite interesting, and I'm very happy to join Conf42 again. And but the slides here I would like to show you is the overhead of Phoebe. Because using these nice features, we actually don't have like a really high overhead compared to other research prototypes. Even we run the experiments in production environment, still like the response time, the CPU load, and the memory usage are quite like slightly improved, but not that much, I would say. This makes it like promising if we do lots of improvements, and then we can still like lower down the overhead and try to improve Phoebe to really learn something more about the system calls or other useful information at the system call level or at the operating system level. Yes, but as a research prototype, Phoebe of course has its limitations, and we need to do lots of future work to explore this field. For example, Phoebe is designed for Java applications. This is because when we do some chaos engineering experiments, we would like to have a multiple layer observability. So we want to collect like the metrics at operating system level, and also the metrics about the JVM, and also some like application specific metrics such as response code, response time, etc. That's why we only evaluate Phoebe for like Java applications. But I think the concepts are applicable to other software stacks. For example, for all kinds of executables in Linux operating system, we can always use Phoebe to monitor its system call invocations and also to summarize its naturally happen errors about system call invocations. So this means like some components can be reused with minor modifications, such as the monitor, the visualizer, and also the system call injector. And the second limitation is the JVM itself. To be honest, it may either create natural system call errors or remediate some errors directly. So this is only our first step, but in the future, I think it would be interesting to explore the interplay between the JVM and the application error handling mechanisms with respect to system call errors. Okay, so the next page is about the summary of our research work on Phoebe. So basically, we propose some like original insights about the presence of naturally happening system call errors in software systems. We also contribute to the concept of synthesizing realistic error injection models for system calls based on an like amplification strategy. So we amplifying naturally happening errors observed in production. And also we implemented Phoebe as a research prototype that like about this concept. So the corresponding paper is called Realistic Error Injection for System Calls. If you are a fan of reading papers, you are more than welcome to give us like feedback about how you think of this paper. Okay, finally, about the Phoebe, the framework, we have already made it open sourced. So if you feel interested in Phoebe, and also if you feel interested in how we address the previous two, the first two challenges I mentioned in the beginning, you can take a look at our Royal Chaos GitHub repo, because KTH is Royal Institute of Technology. So we have this Royal Chaos repo, which contains all kinds of different our research work in the field of chaos engineering, papers, source code, and also experiments. So feel free to take a look and also create issues if you have like further questions. Okay, so as a summary, during this talk, I presented like a short demonstration. So we had an overall picture about the system call invocations and the naturally happening errors behind it. Then we proposed the design of Phoebe, which takes the naturally happening errors as input and automatically synthesize realistic error models for chaos engineering experiments. In the Phoebe, the most interesting or important idea is application error rate amplification. So we have different strategies and we have categorized the errors into different types. And also we did some evaluation experiments on Phoebe on different applications. So we have some interesting findings, and of course, based on the findings, we have summarized like the cool ideas and also the limitations of Phoebe. And the last point is to take a look at our Royal Chaos GitHub repo if you feel interested. Basically, that's all of my talk today, and I hope you enjoyed it. If you feel interested, please, you are welcome to contact me at any time. I look forward to discussing more with you, and we keep in touch. Thanks a lot. Have a nice day.